Question 3, I can see it is coming from organic chemistry. Alkenes undergo an addition reaction with a 1-to-1 mixture of carbon monoxide and hydrogen to form aldehydes. The figure here shows the reaction of propene with 1-to-1 mixture of carbon monoxide and hydrogen. Okay, so in the books of Cambridge, you are not going to find this one here, but they describe for you something here to base on to answer the question. A Roman 1, define an addition reaction. So in an addition reaction, we are seeing that things come together more than one, then to give you one product. So you put two things together. What is to add? Let's say like I'm having a 4 plus a 5, then I get a 9. So I have more than one thing, okay, to add, then to get one. You see that? So I'm going to write, this is a reaction. This is a reaction where 2 or more compounds, 2 or more compounds or reagents. Actually, let me just put reagents because you can have an element reacting and an element is not a reagent, a compound. So 2 or more reagents or substances, okay, form only one product. So only one product is very, very important. Okay? That is that. Then Roman 2, aldehydes A and B are structural isomers. State the type of structural isomerism shown by A and B. Now, we can see this group here is on, there is a carbon here, here, and here. Let's say this group here is on this first carbon. I'm taking this one as the first carbon, okay? This is now, I'm taking this one, the CHO, as the functional group, okay? So I'm not counting that carbon. But now, this one is on this second carbon here. So if it is on the second carbon here, and then we see this one is now on this other carbon. Okay, let's say this is carbon 1, carbon 2, carbon 3. So this one is on carbon 1, 2, and 3. Now here we are seeing 1, 2, and 3. Now it is on the second one here. So this one is about the position. So we are seeing the position of the functional group. So this has to be positional isomerism. Positional isomerism. Just like that. And then the next one, name A. When we look at A, how many carbons? 1, 2, 3, then 4. So 4, that is but. Since it is an aldehyde, then it has to end with Al. So that is butanal. Butanal. Okay. Then next, they are saying that Roman 4, the complete reaction of propene with 1-to-1 mixture of carbon monoxide and hydrogen produces A and B only. The product mixture contains 96% of A and 4% of B. Calculate the mass of A produced in the reaction when 5 times 10 to the power of 3 kilograms of propene is used. So we need now to know what is formed here. Number 1, you need to get the MR, okay? Let's begin with the MR of butanal. So butanal is CH3, CH2, CH2, CHO. So this one is going to be, there are 4 carbons, so 4 times 12, and then plus hydrogens, how many are they? 3, 5, 7, 8. So 8 times 1, 8 times 1, and then plus oxygen, of course it is 1, so times 16. So I have 8 plus 16, that is 24. 24 plus 48, that one will give us 72. Okay, now this means that 72 grams of butanal contain 1 mole. So what will be now the moles of butanal? Okay, so moles of butanal. What will be the moles of butanal? Moles of butanal, when you check back here, 1 mole of propene gives 1 mole of butanal. That means the moles of propene we get will be equivalent to the moles of butanal which are produced. Okay? So here I'll say moles of butanal produced will be equal to moles of propene. Moles of propene used. Now, what will be the moles of propene? So propene is here. C propene is this is an alkene, so C3 then H6. That means its MR is going to be 3 times 12, which will be 36, then plus 6 times 1, 6 times 1, that is 6. So 36 plus 6, that will be 42. Okay, so meaning moles of propene, they are going to be mass, which is given here, 5,000. So 5,000, then, and it is kilograms. Mass here has to be in grams. So again, times 1,000, then we divide by this 42 here. Okay, so that will be the same moles for butanal. Then from there, those moles that we have gotten, we can now find the mass. So mass of now butanal is going to be equal to the moles that we have gotten here times the molar mass. Okay, so times 72. Because here we got it as 72, so times 72. That will be the mass of butanal. And they are saying mass of A, which is, I think, butanal. Okay, but that one is not going to be the answer, because they said that the product mixture contains 96%. So that means the mass that I get here, then I will have to multiply by 96%. So what comes out is not exactly this, but 96% of it, so times 96 over 100. So altogether, what do we get? 5 million, then we divide by 42, then times 72, then times 96 out of 100. So this one gives us 822 up to, that is 4.29. So we have 82285.7, then 1, then 0.429. Now these are grams, but here we are seeing kilograms. So this one will be 8228571.429 divided by 1,000. Then it becomes kilograms. Okay. Then here we are going to move 1, 2, 3. So it will come there. And then we have 8, then 2, 2, 8, then 0.57 and the rest of those values. But if I write to, let's say, 4 significant figures, I can write 8229. So I'm just going to write 8229. And then I say 4 significant figures. You can even write to 3 significant figures. That means you round this one off to this, and then you have 8 to 30. Okay, this will be 3 significant figures. Part B, A and B show reactions typical of aliphatic aldehydes. Aliphatic, these are straight chain. Okay, or we don't have the rings, the benzene rings. It may not be straight, I mean, because we can also have the cyclo. Okay, so aliphatic. Roman 1, A undergoes a nucleophilic addition reaction with a mixture of hydrogen cyanide and potassium cyanide, forming compound C. That is what we call hydroxynitriles. Okay, it's an addition reaction. That's why they are even saying addition, but the mechanism is nucleophilic. So what you are adding there is a nucleophile. Complete the diagram to show the mechanism of for this reaction. Include charges, dipoles, lone pairs of electrons, and carry arrows as appropriate. Draw the structure of the organic intermediate. Now we need to bring this cyanide here, negatively charged. It has a lone pair. Now, since oxygen is more electronegative than carbon, it will tend to pull the bonding electrons towards itself. Therefore, it will attain a partial negative charge. And carbon here, which appears to be losing electrons, will now attain a partial positive charge. So it appears to have lost electrons, and this one is rich in electrons. Therefore, it donates those electrons to it, and by coming here, then this one here is broken off. The pi system here is broken off, because whenever there is a pi system, electrons are moving from, let's say you have a compound here and then the oxygen here, so there is a sideway overlap, okay, of this. So they bend here and they bend here, then electrons are moving like this in that circle. So there is limited rotation because of this, okay. So when electrons come in here, then they break this pi system, so it has to open up, okay. So when it opens up, then we are going to have a hydrogen here, then carbon here. Then since this one has now received electrons, by the way, these arrows here show the flow of electrons. So they moved from here, then they came to the oxygen. Now oxygen there becomes negatively charged, fully negatively charged. Then here, the cyanide, okay. Then here we have C3, then H7. Now oxygen here has gotten a lone pair of electrons. Then it can come for the hydrogen ion that comes from the hydrogen cyanide, okay. Then from there, we have that. Or if you don't do that, you can put hydrogen cyanide like this, and then this one breaks off. But then when you do that, then you will add the cyanide here, okay. So, but I'm just going to use the hydrogen ion here. And that is that. So there is a full mark for this one here, the intermediate. You have to be very careful. So if you forget the sign here on the oxygen, you go. Then Roman 2, table 3.1 shows information about 3 experiments involving B. By the way, for B, what do we have? B, we have, yes, this one here. It's an aldehyde. They're just isomers. Now, the reagents are here. Solution turns from orange to green. That has to be acidified potassium dichromate, orange to green. So we shall put here acidified potassium dichromate solution. You can actually just represent it like that. Then a silver mirror forms on the sides of the reaction vessel. That is Tollens reagent. We call it ammoniacal silver nitrate, Tollens reagent. This one gives a positive test with aldehydes, but not ketones. The other one is Fehling's solution, ammoniacal copper 1 nitrate. This is ammoniacal silver nitrate, okay? Now, bromine here. So bromine, water. This one gives a positive test for these unsaturated compounds like alkenes. So if I have, let's say this is an alkene here, this one, as it draws, it has no charge because these two have gotten the same electronegativity, so dipoles cancel. But as it draws nearer to this one here, which is rich in electrons, negatively charged, so it will induce a partial positive charge, and then this one will get a partial negative charge because electrons will be repelled away from this, and then they come to this side, so it will appear as if it has received electrons. Then this one can come to that, and then we can have CH2, maybe the Br attaches to this carbon, then you have CH2 then plus here. This is the carbocation, and then the other, this one here, remember there is breaking of this bond here, and then this one will donate its electrons to this, then you will get Br, CH2, CH2, Br. Now this molecule here has been broken down, the bromine, because of this what? Unsaturation of this compound. So this one, we are seeing CHO. Okay, then there was a carbon, then this was CH3, and then this was CH3. So the unsaturation is between the two carbons, not here. Okay, it's between the two carbons, the double bond between the two carbons. So this one is not going to give a positive test. So we just say no reaction. So this one is true for alkenes. They will give a positive test with bromine, which is a brown liquid, and it turns colorless. Why? Because they have broken this bond between the bromine atoms. B, this is its molecular formula, is oxidized by acidified potassium manganate 7. Complete the equation for the reaction. Use O here to represent an atom of oxygen from the oxidizing agent. Now, when you oxidize an aldehyde, you get a carboxylic acid. Okay, you get a carboxylic acid. First, I can write this. This is CH3, then there is CH3, and then CHO. This is the B they gave us. Okay, now when I add their oxygen, this oxidizing agent, I'm going to get a carboxylic acid. So CH3, this one here is COOH, then H, then CH3. So what has been added? There is one oxygen added here. Okay, so I'll put plus O here. Then we are getting, there is nothing that has been added. It is just one oxygen just here. So meaning oxygens from here, they are going to be 2. So I will just write C4, then H8, O2. As simple as that. Roman 4, C is a chiral molecule. This is C here. That means one atom has gotten that one of the carbon atoms must be having 4 groups which are attached to it. Circle any chiral centers in the structure of this. When you begin from here, this group is different from this, is different from this, and is also different from this. So this simply implies that this one is a chiral center, a chiral carbon. This one has 2 which are the same, even this one here, this one 3, so the rest are not. So we are just supposed to put a circle there. They are saying that when propene, that is part C, reacts with carbon monoxide and an excess of hydrogen, an alkane and a mixture of alcohols are formed instead. The alcohols are isomers of each other. Suggest the molecular formulae of the alkane and the alcohols that are formed under these conditions. What is the molecular formula of the alkane and then that of the alcohols? Now, from the beginning of this question, we have propene here reacting with carbon monoxide. Do you see that to form the aldehyde here, 1 carbon was added? This is 1, 2, 3. This is 1, 2, 3, 4, right? So then, now this is butanol. Then with excess of hydrogen, then this one is going to be reduced to a primary alcohol. You see that? So that means what we are going to do here when we get back, okay, when we get back to this one, they are saying formula of the alcohols. So first of all, for propene, you are going to form butanol. Then butanol is going to be reduced to a primary alcohol. The primary alcohol can be butan 1-O or butan 2-ol. That's why they said that the alcohols formed, there is somewhere they say the alcohols are isomers of each other. So alcohols, remember the carbons here are 3, so we have added, they become now 4. So the molecular formula, we have CH3. Let me first write the structure formula: CH3, CH2, CH2, CH2OH. Then the other one will be CH3, CH2, then CHOH, and then CH3. This is butan 1-O, this is butan 2-O. They are isomers of each other. How many carbons are here? There are 4. Then hydrogens, 3, 5, 7, 9, 10. Okay, so hydrogens are 10. I'll then put here hydrogen 10 and then 1 oxygen. Then the formula of the alkane, Now, you cannot get this one here and then you reduce it to an alkane. You see that? So the alkane is going to be formed from propene when, let's say, a molecule of propene here, okay, now reacts. Remember they said an excess of hydrogen. So it will react with hydrogen here. Then you will get propane, CH3, CH2, CH3. That is propane. So this one, the molecular formula is going to be what? Remember for alkanes, it is CN, H2N plus 2. So hydrogens are 8. So we shall have C8, C3, then H8. That is what we are going to have there. Then part D, the reaction of ethene with a 1-to-1 mixture of carbon monoxide and hydrogen is shown in equation 1. Okay, this one here. And we can see that we are forming from alkene. So 2 carbons, now here they become 3, then we form propanol. At atmospheric pressure, a cobalt-based catalyst is used in this reaction. State and explain the effect of using a catalyst in the reaction. It increases the rate of a chemical reaction. So I can say a catalyst increases the rate of reaction. And how does it do it? By providing an alternative pathway. An alternative pathway with a lower activation energy. Remember, when the activation energy is too high, then the reaction is slow. It never reduces, a catalyst never reduces the activation energy, it just provides a pathway with a low activation energy. Roman 2, explain why the yield of propanol here increases when the overall pressure of the reaction is increased. If we can fall back here, when you increase the pressure, look at the number of gas moles this side. There are 3, and this one is 1. Okay? And we know that pressure is inversely proportional to volume. So when you increase the pressure, the volume has to reduce. And volume is directly proportional to the number of moles. So when you increase the pressure, that means the side with more gas moles is going to react. And then the reaction will shift to the position, the position of equilibrium is going to shift to the side with fewer gas moles. Okay, fewer gas moles, which are this side. You see that? So it will shift to this other side. So that's why you are going to get more yield here. So therefore, I will come back here and I say that the position of equilibrium shifts to the right side with fewer gas molecules. So that is that. Then next, problem 3, use the information in table 3.2 to calculate the enthalpy change here of the reaction. So we have this and we are given the enthalpy change of formation for ethene, then carbon monoxide, and then this. So enthalpy change of formation, we are looking at formation of that 1 mole of a compound from its elements, okay, in standard states. So our reaction here is C2H4, then plus the carbon monoxide, then plus the hydrogen. Then we are getting CH3CH2CHO, which is gaseous. And then all of these ones are coming from which elements? We have carbon, we can see hydrogen, which exists as a diatomic molecule. We also have oxygen, diatomic molecule. Okay. Carbons are 3 here, so I can put a 3 here. Hydrogens are how many? 4 plus 2, 6. Even this side, they are 6. So I can put a 3 here. And then oxygen, of course, we are seeing 1, 1. So, but whether you balance these ones or no, it doesn't matter. So hydrogen is gaseous, then this one is a solid. Now, I'll put this one in this one here. We are going to use the Hess's law. So we are getting this one here. We also get carbon monoxide, but the enthalpy change of formation of hydrogen, since this is an element, that one will be 0. Okay, so I don't put it there. And then the enthalpy change of formation of this one is also given. So what is for propanol? That is negative 187. Then for carbon monoxide, it is negative 111. And then for ethene is positive 52. Okay, now here we have DHR, enthalpy change of the reaction. Now what I need to do is to follow clockwise is equal to the anti-clockwise. So if I go like that, then I will say 52, then plus negative 111, then plus DHR, then will give us this one, which is instead going like that, negative 187. So meaning DHR is going to be equal to negative 187. Take this one, the other side, it becomes a minus. So minus 52. Take this one, the other side, it's a minus, so it becomes a plus 111. So what do we get altogether here? Negative 187 minus 52 plus 111. That is negative 128. So negative 128 kilojoules per mole. Roman 4, the reaction mixture is cooled to collect this one here as a liquid. Identify all types of van der Waals forces that are present between molecules of this one here. Okay, now we have, since this one is a molecule, then we have the van der Waals forces, okay, in between the molecules. So we call them the instantaneous dipole. Then induced dipoles. We can even write it as IDID. When you write it like that, they give you no problem. And then we also have the permanent dipoles. Permanent dipoles. Then this one you can write it as PD, not DP, which is PD. Now, why are there permanent dipoles? It's because we have this one here, the carbon, and then the oxygen. So this one is partially positive, and then this one is partially what? No. That one is partially negative because it is more electronegative compared to the carbon. And then this one will be partially positive. Okay, because of this dipole here, it is permanent. It is permanent there because oxygen is always electronegative compared to that of carbon. So that is that.